project with Nicola and some other people we work on now. But I decided to choose another story, which is a very, very long story. It started 130 years ago, and the modern part of the story is maybe already 25 years old. Many people are involved, many results are obtained. It's a very interesting story, I think, because it unites geometric measure theory and harmonic analysis and complex analysis. And I'm in some structural panic because there's so much material, but I will just start, and if in 55 minutes you cannot speak about 130 years of development, but I will start, and the way I finish, I finish. So maybe it will be in the middle of the phrase. Okay, so this all started with the question of Penlever. So let me formulate this question in the modern language. So Penlever asked the following question: given a closed compact set on the plane, when you can say that if you consider functions which are analytic in the complement, bounded, and zero at infinity, when you can say that there is only one such function, namely zero function. So the simplest example when you can say that is when E is just one point. If E is just one point, the bounded analytic function outside of the point removes the singularity, which we teach our complex analysis students. It becomes analytic everywhere, and being bounded, it is constant, because entire functions which are bounded are constants, and being zero at infinity, it can be only zero. So the point is a removable singularity for such functions, for bounded analytic functions in the complement of E. If E is a point, then you remove the singularity. Well, Penlever noticed that you shouldn't just say a point, it can be this. So what does it mean H1 of E is zero? So H1 is a Hausdorff measure of dimension 1, and I don't want to give the formal definition, but H1 equals 0 means that you can have a collection of disks covering this set E, such that the sum of radii is less or equal than epsilon, and epsilon is an arbitrary positive number. So you can cover it by such small collection of disks. The sum of radii is less than epsilon for any epsilon. But there is a formal definition of what is H1. Sometimes it's called length, because for nice sets, it's really just the length of the set. In principle, it's just a measure on the plane. It's not sigma finite on the plane, but on some sets it's sigma finite, so it's a very nice measure. Anyway, so this is what Penlever proved, that if set is thin in this sense, H1 E is 0, then gamma of E is 0. So gamma of E is the quantitative version of what I said. So gamma of E is 0 means that there is only one function which is bounded analytic and 0 at infinity. Well, what does it mean gamma of E is 1? So here is the definition of gamma of E. So you take all possible functions less than 1, analytic in C minus E, 0 at infinity, and compute this stuff. It's called derivative at infinity. So you take all such functions, compute derivative at infinity, take absolute value of this derivative, and take supremum over all functions normalized here. And this is a number. This is a number, and for compact sets, it will be always a finite number. And so we were mostly interested in whether it's 0 or not, but we're also interested in this number as it is. Okay, so here is this Penlevet thing that if H1 is 0, if the length of the set is 0, then gamma of E is 0. And of course, he asked the opposite question. Is it true in the opposite direction? Is it true that if gamma of E is 0, then the length is 0? So if Alfors noticed, you see, as I said, it's 130 years old. So in the 40s, Lars Alfors noticed that gamma of E is 0 is a local condition. You don't need functions analytic in the whole C minus E. It just means that the function analytic in some disk minus E is also analytic on the whole disk. Okay, bounded. It should be bounded. It's very important. So if it's analytic, it removes singularity. It doesn't notice that there are some singularities. It automatically becomes analytic everywhere. So anyway, so that's small part of the answer. If the length is 0, then the set is removable. Okay, but the other part of the answer should be the opposite arrow. And actually, Penlevet didn't exactly ask this question: is it true that gamma of E is 0 implies that length is 0? He just said, please describe geometrically what does it mean that gamma of E is 0. So that would be a great answer. That if it's, then it will be if and only if, right? And it's geometric thing because length is a geometric notion. So in 1946, Danjois answered the question of Penlevet in the affirmative. He proved that yes, removable means that the length is 0. In 1956, Vitushkin proved that no, he constructed a counterexample. Okay, so Vitushkin was right. That's not the answer. What actually Danjois proved is that if this E has an extra property that it lies on the line, then yes. Okay. But that's a very small piece of answer. So Vitushkin constructed a set which is removable and has a positive length. His construction was complicated. It was a difficult construction. But in 1970, John Garnett constructed a simple set which has this property. It's removable, so gamma of E is 0. It's like point. It's like a point. If you have bounded analytic function in the neighborhood of a point, it's analytic also on this point. Well, here is this very thick point. It's the Garnett counter set. So its gamma of E will be 0, but its length will be finite and positive. So the length will be positive and finite. So this set is one, yeah, any questions? This set is 1/4 counter set. So how you construct it? Well, it's on the picture. Here it is. So you take a unit square. You consider 4 corners of squares of size 1/4. And throw away the cross in the middle. So you are now left with 4 squares. And then you repeat the procedure. So the next generation will be squares of size 1/16. These small guys. The next 1/64, etc. You just construct counter set. This counter set is very easy to see that its length is positive and finite. this Hausdorff measure is positive and finite. But it turns out that it's removable. It's like 1 point. And the proof wasn't too easy, but it was a short paper. It was a short paper. So we see that if E, like in Danjois case, has a 0 length, and it sits on the line, no, 0 length is always gamma V 0, but if it sits on the line and has a positive length, then gamma V's should be positive. It's on the line and has positive length. Then gamma V should be positive. But if it's spread out in the plane in this counter fashion, it can have positive length, but 0 analytic capacity. So this is the part of the two pieces of information people have in 1970. So what does it mean? Can we somehow generalize that to observations? So one observation that if E lies on a nice set and has positive length, then gamma is positive. And if it lies on a not so nice place and length is positive, then gamma can be 0. How to unite these two things? Well, it turns out that actually there are 2 different answers. So there are 2 different cases, and the answers are completely different in these 2 cases. So the 2 different cases are the following. So the first case is when we a priori know that the length is positive and finite. Well, when the length is 0, we don't need to do anything because already Penlevé noticed that then analytic capacity is 0. So we need positive and finite. And the second case, when the length is infinite. You can ask now why you consider always threshold 1. Why it's H1, H1, H1. What if, for example, Hausdorff dimension of this set is strictly bigger than 1? Well, this is easy, very easy. So as soon as Hausdorff dimension is strictly bigger than 1, then the set cannot be removable. Its analytic capacity is positive. Okay, it's thick, it's too thick to be removable, and this is very easy. So this is Frostman's lemma, so it's a sort of, today it can be almost called triviality. So everything is about dimension 1. And dimension 1, again, has 3 cases. Length 0, then we know, Penlevé already answered. Length positive and finite, that's one case. And length infinity is another case. And it turns out that the answers in these 2 cases are completely different. And so we first consider the first case. It's very interesting. And actually, what happens in this case is called Danjois problem. I will formulate Danjois problem in a minute. But first, let me remind you so-called structural theorem of Bezikovich. So it's a theorem from geometric measure theory, and it gives a structure to such sets. So all such sets have structure. And the structure is the following. Every such set can be decomposed, basically canonically decomposed, to 2 pieces, R and N. N is called totally irregular in the sense of Bezikovich, and N is the part of, it's, you know, the set is called totally irregular in the sense of Bezikovich if it has the following property. If you intersect it with any rectifiable curve, rectifiable curve, if you intersect it with any rectifiable curve, then the intersection has 0 length. So this, one can think that it's something very strange, but no, it's not very strange. It's not very wild. So this is the example of N. This 1/4 counter set of Garnet is a typical irregular, totally irregular in the sense of Bezikovich. It's impossible to draw any rectifiable curve such that it would intersect this counter set on something more than 0 length. So this counter set is invisible for rectifiable curves. You drop any rectifiable curve on the plane, it will intersect it only on 0 length. And this ends, this totally irregular in the sense of Bezikovich, they're basically of this type. Of course, it's just an example. They can be of more complicated nature, but that's basically how they look like. Okay, and the second part is exactly totally regular. What does it mean, totally regular? Well, it means that you can write it as the union of its intersection with countably many rectifiable curves. Of course, there can be some dust, some garbage, but this garbage should have only 0 length. So your set can be, so it's a super beautiful structural theorem for very, very general sets. It's due to Bezikovich. It's in the 30s, so 1930s or something like that. Okay, so structural theorem of Bezikovich. And now I think we can formulate ourselves this problem of Danjoy-Vitushkin. So if we are in this mode, in this regime, that H1 is positive and finite, then hey, it's a good hypothesis because it satisfies both pieces of puzzle which we know at this time. Then the set is removable if and only if it's totally irregular in the sense of Bezikovich. So that's a very good conjecture. Okay, because if the set was on the line, then its removability was exactly 0 length. So this piece of the puzzle fits. And if it was totally unrectifiable, the example was like that, and it was removable. So it looks like a good interpolation between two examples we know. Okay, so let's reformulate this problem to make it sound a little bit easier. So to prove it, it's necessary and sufficient to prove the following result. So the set is not removable for bounded analytic function if and only if there exists rectifiable gamma such that the length of intersection is positive. So this claim is exactly equivalent to the problem of Danjoy and Vitushkin. Now it's very easy to see after Bezikovich structural theorem. You apply Bezikovich structural theorem, and then it reduces this problem to this claim, which sounds a little bit easier. So the set is not removable. Its analytic capacity is positive, if and only if essential part of this set lies on a rectifiable curve. Or let me translate it in a little bit more picturesque terms. If there is a rectifiable curve such that it really intersects this set on some positive length. Rectifiable can even be replaced by an easier thing, Lipschitz. It's equivalent. It's not trivial that it's equivalent, but it's equivalent. Or even C1. So the question is, we are given a set, positive and finite length, whether it's removable if and only if you can draw like a smooth curve which will intersect with set on the positive length. In other words, let's think that this set are banks, and then non-removability, positive analytic capacity, means that you are a bank robber, you take a motorcycle, and the finite time you will be able to rob sufficiently many banks. So motorcycle, because motorcycle can be only make a connected path and smooth sort of. So I don't say helicopter or something, because then it wouldn't work. So this is why sometimes it's called traveling robber problem. So it has two parts. So let's call the left part analysis, because it's about analytic functions, about complex analysis, about removability of set for bounded analytic function. And the right-hand side obviously should be called geometry, because it gives a geometric answer. And so we have two arrows, one from geometry to analysis, one from analysis to geometry. Both should be proved. This is very typical for this circle of questions. They have analysis, geometry, and both paths should be proved. Philosophy, there are many such questions. Some of them are answered, some of them are not. Philosophy of this is that geometry to analysis is usually difficult, but analysis to geometry is usually one order or two orders of magnitude more difficult. So this direction, analysis to geometry, get the geometric information from analytic information, is usually super, super tough. And another name which I learned from my professor of mathematical physics from Leningrad University is that it is called free boundary problem. Because you need to establish a certain geometric property of a set about which you know almost nothing. Well, almost nothing is a little bit, I mean, who knows what does it mean, almost nothing, but that's free boundary problems understood in a wide sense. There is a strict sense, which is, we don't consider here, but in the wide sense, it's this type of claim from analysis to geometry. But geometry to analysis is usually not easy also. For example, in this case, it required the solution of Calderón's problem. So the problem of Calderón was, suppose we are given a Lipschitz curve on the plane, so Lipschitz, and you consider the Kashi integral operator. So we will see this Kashi integral operator soon, so I'm not writing it now. So you consider the Kashi integral operator on this Lipschitz curve. Please prove that this operator is bounded in L2 on this curve. What kind of L2, what kind of measure? Well, it's a Lipschitz curve, so there is a natural measure, which is length. Okay? So that was Calderón problem. It was open for many years. Calderón proved it himself for a Lipschitz curve with small Lipschitz constant. Finally, it was proved by Koifman, Meyer, Koifman and Meyer, Then there was a proof by Peter Jones and Stephen Sams. There were other proofs. It is a big, interesting piece of analysis. It's not easy. Well, it was Calderón's problem. But it was direction in so-called easy direction. Well, it wasn't easy. But I'm just saying that to emphasize that the opposite direction, analysis to geometry, made much more difficulties. So let me kind of prove it. Of course, there will no proof in any sense, but I will show the plan how to prove this difficult error. Yeah, so after that, as you understand, this will be proved, check mark. And so Vitushkin conjecture, Danjoa-Vitushkin conjecture will be proved. Okay, so by the way, who proved that? Well, there were two groups of people who simultaneously proved this thing. So proving Danjoa-Vitushkin conjecture. So one was Pertti-Mattila and Guy David. And another group and another proof was my friends Nazarov, Trail, and myself. So it happened practically simultaneously. Both proofs are pretty long. So these are two papers. It's in Revista, and they're together like 200 pages. This is slightly shorter. It's one thing. It's like 70 or 80 pages. And the proofs are different. Okay, so let me kind of indicate a plan. So we need to start with analysis. This is analysis. Set is not removable, and we know about this. We know about the set that. So two things we know about the set. We need to prove that we can build a robber, that we can build a motorcycle guy or rectifiable curve such that it will chop a positive length from E. So first step is easy. First step is easy. So if these two things with us, then there exists a complex measure, and there exists a complex measure on E, complex measure. It's very important. Such that its complex of E is not zero, and such that the Kashi transform of this measure is a bounded function, which is not a zero function. Okay, so that's an easy step. If you have this part of analysis, then you can construct a complex measure with the property that its Kashi transform is bounded, but it's not trivial. It's not zero. So it's a very easy step. Well, the second step sounds like something really strange. So given that you have a complex measure such that Kashi transform is bounded and not identically zero, you have to prove that there exists a positive measure. So measure is positive. And of course, total mass is positive, such that Kashi transform is also bounded. So given a complex measure, the only thing you need to prove that there exists a positive measure with the same properties. Now, why is it a little bit, how to say, well, kind of incredible? See, if you have a complex measure or even real measure, just real but signed, not positive, you have much more chances to have Cauchy transform bounded because of cancellation of charges. And suddenly you claim that then you have a positive measure, meaning that it has no cancellation of charges, such that the Cauchy transform is still bounded. So it basically philosophically says that Cauchy transforms of measures are bounded not because of cancellation of charges, but by some other reason, which we don't know. Okay, so another thought when you see such a claim is that, you know, such claim can be only of two types. It can be trivially false. You just construct counterexample just in 2 hours, or it should be trivially true. You just prove it very simply in 1 hour. Well, it's neither. It's definitely not trivially false because it's not false. There is no easy proof of that. It's a very, very difficult theorem. So the next step is again difficult. It says that if you have such a positive measure, then you can, so harmonic analysis starts. Then you can, well, harmonic analysis was already here, but here it's even more harmonic analysis. You should prove that if you have such positive measure, then a certain operator is bounded. This is what harmonic analysts are doing. They're proving that some operators are bounded. And usually these are singular operators. So here is the operator. So you have this measure on E, positive measure on E. So you have L2 with respect to this measure. And take a function from this L2 and consider this singular operator. So call it T mu F. So you have to prove that from just this property that Cauchy transform is bounded, you should prove that this is a bounded operator from L2 to itself. Okay. So this has been proved by Nazarov, Trail, and myself, and so this paper in ACTA. So we have this operator, which is bounded. So we started with non-removability of gamma and positive finite length. And we already constructed a certain special measure on set E, positive, such that operator, Cauchy operator, this is Cauchy operator. I promised that we'll have Cauchy operator. So that's the same operator than in Calderòn problem. But in Calderòn problem, E was a Lipschitz curve. Now E is nobody knows what, some idiotic set. Okay. And in Calderòn problem, measure mu was the arc length on Lipschitz curve. And here it's just some measure, which we again don't know what it is. Okay, but it's positive. So it's a Cauchy operator. So we came to another analytic thing. Cauchy operator is bounded. It's still no geometry. We need to prove that there is a rectifiable curve which intersect our E on positive measure. So far, there is no rectifiable curve. There is some abstract measure and abstract operator which is bounded. Okay, next step is the following. It's a simple thing. So if this operator is bounded, then there exists some positive delta and some subset of E, but non-trivial subset, such that your measure on this subset is equivalent to the length, to H1. And equivalence is pinched between this positive delta and number 1. Okay, it's an easy step. So from this easy step, you conclude again easily that a slightly more easy operator is also bounded. Not the Kashi operator with respect to some enigmatic measure mu, but the Kashi operator with respect to H1. So you conclude that there exists a subset of positive length, H1 of E prime is positive. E prime is subset of your E. And the Kashi operator with respect to length on this E prime is bounded. E prime is still who knows what. It's absolutely crazy set. You cannot even understand how it looks like at this moment. But your information that you found a positive length set on which Kashi singular integral is bounded with respect to measure, which is H1. So it's almost like Calderòn problem, but in Calderòn problem, there was an extra information that this H1 was the arc length measure on Lipschitz curve. So there's no Lipschitz curve at this moment. Okay. So the next step, so far it was us. The next step is not us. So next step was known. It's super beautiful, very non-trivial, elegant step. It says that if this operator is bounded, then something geometric happens. Something geometric happens. And this geometric I wrote as this formula. So in words, they say that Menger's curvature is finite. So Menger's curvature of the set E prime is finite. So what is Menger's curvature? So you take 3 points, any 3 points, any triple point on E prime. So you consider E prime, cross E prime, cross E prime. For 3 points, you can always construct a circle which comes through these 3 points. Maybe this circle is infinite, they can lie on one line, but it always has a radius, maybe infinite radius. And we call this radius R, Z1, Z2, Z3. So you consider the function R1 over R squared, Z1, Z2, Z3, and you integrate it over this length on E prime, E prime, E prime. If this thing is finite, you say that Menger's curvature of E prime is finite. So we concluded that Menger's curvature is finite. Who did this step? So this step from here to geometric thing that Menger's curvature is finite, it's so-called Melnikov's formula. It was invented by Mark Melnikov in the end of 80s. It's amazingly beautiful how you get from here to here. But it takes like two pages. It's amazing observation. It's a kind of sort of unbelievable thing, but that's what Mark did. Meaning. So what is this meaning that it's finite? It's finite morally means that 1 over R squared is not very large. Or rather, so it's small basically, right? It also means that R squared is very often large. large means that Z1, Z2, Z3 are almost on the line. So it means that there are so many triples of points such that the geometric kind of situation is like that. The triangle is very much like a flat triangle that you have this curvature finite. And now it's easy to believe that if you have many such triples of this type, that maybe it means that there exists a rectifiable gamma such that intersects the C prime on a positive measure. Because there are many, many triples which are so flat. It's again not us. It's super difficult geometric thing. It's Guy David and Jean-Christophe Léger. So these are papers in Annals of Mathematics in the I think late 90s. So that's true. So if you have finite Menger's curvature, you do construct a rectifiable curve such that intersects your set on positive length. So, and that finishes the proof of Danjois-Vitushkin conjecture. So the second case, so we're still on the plane. In the second case, the answer is completely different. Well, first of all, there is no kind of real answer. Well, there is an answer, but I don't even want to tell you because it takes 15 minutes to explain the answer. So there is no, I mean, easy geometric, there is no easy geometric way to describe such sets with gamma of E positive. There is no easy way to describe geometrically such things, but there is no easy way. So I don't want to spend time. But the answer is definitely very different because there is a counterexample. There's an example of Peter Jones and Takufumi Murai, which proves that there exists a compact set with infinite length, non-removable, but such that for any rectifiable curve, again, intersection is 0. It's invisible for rectifiable curves. So it also has this property, BU equals 0. So let me explain what is BU. So here is BU. BU stands for Buffon needle probability. So you have your compact set and you drop very long, thin needles on it and you compute the conditional probability that it will intersect this set if it intersects a certain big disk in which this set lies. So in mathematical language, it's the following. So here is your E. You project it on a line which has angle theta with a fixed axis. You project, you compute the length, and then you average over all angles. So it's a sort of a length also. It scales as a length. It's actually called Favart length because Favart also introduced it. So it has two names, Favart length and Buffon needle probability. For example, for this counter set, which we considered above of Garnet, we know that usual length is between 0 and precisely bigger than 0 and less than infinity. But this new length will be 0. So if you project the counter set I constructed above on almost every line, the length of projection will be 0. Okay, so there was another problem. Is it true that here is another geometric characterization? So suppose we have this condition. Again, we come back to the first case when length is strictly between 0 and infinity. Is it true that non-rectifiability, non-removability, so the existence of non-trivial analytic function and bounded outside of it, is the same as before needle probability is positive? The answer is yes. And so again, this is us. And again, as soon as you have here infinity, the answer is no, by the example of Jones and Murray. So yeah, maybe one funny word, something very interesting about this. So the fact that for this counter set, Favart length or before needle probability is 0 was known long ago. It's actually was proved by Bezikovich. Bezikovich proved much more general result, but it follows from his result. But what about quantitative version? What does it mean, quantitative version? So let's start to construct this counter set and stop at stage n. So you will have 4 to the n small squares of size 4 to the minus n, and they will sit in counter position. Then you project this on line angle theta. You will have some positive thing. Then you change theta and average. So you compute before needle probability not of the counter set, but of its approximation, of the neighborhood of the counter set. So obviously it will go to 0. So it's some epsilon n, which goes to 0. So it's really very tough question, very interesting, and not resolved. How fast epsilon n goes to 0. So from one paper of tau, it follows that it goes to 0 with this speed. So what is logarithm star of n? Logarithm star is the following function. You take a logarithm n, then log n, then log n, and you continue in this fashion up to the moment when you drop below 1. The number of logarithms you need to do that is logarithm star of n. So it's super slowly growing function. Maybe it's the least growing function on Earth or something like that. Well, anyway, in a series of papers with Isabella Laba, Fyodor Nazarov, and my former student Matt Bond, we actually proved that it is like polynomially small, alpha. But we don't, well, we know that alpha is, we can prove for alpha less than 1/7, but we have no idea what is real alpha. So it's in fact, it's a certain problem about Kakeya sets. Kakeya sets on the plane, but in counter directions. Counter directions. Well, we know that questions about Kakeya sets are very difficult. So that's, of course, on the plane there should be easier, but it's a specific one in counter direction. So we know something, but we don't know everything. Okay. I wanted to say maybe one word about this theorem. Why, if we have complex measure with bounded Cauchy transform, then we have positive measure with bounded Cauchy transform. It's sort of the most difficult part of the proof. Well, unfortunately, I can only wave hands, but I will say something that we have a quantitative version of that. What does it mean, quantitative version? It means that suppose this analytic function is bounded by absolute value by 1. And we also construct another Cauchy transform, and it will be also bounded by 1. Then the simplest one is just to take mu equals 0. But this we're forbidden to do because we need positive measure. So we need to estimate this measure from below. And probably this estimate will be very bad. Well, this is a quantitative version. Yes, we can estimate this measure from below, and it is bad. So this is the estimate. So the first term of this estimate is nu of E, which is supposed to be non-zero. It's given. And the second part is a funny thing. You kind of measure this absolute value of this complex number divided by total variation of measure. Total variation can be so much bigger than just nu of E. So this fraction is super small, but positive. And then it raised to some very large power. So it's a bad estimate. But this estimate was good enough for Xavier Tolsa to use it to prove very famous Vitushkin's conjecture. So Vitushkin was interested in this analytic capacity from his approximation research, and he needed this property. So semi-additivity of analytic capacity. You see, the usual capacity which we're used to, they have positive kernels, and then semi-additivity goes from definition immediately. Even very complicated capacities, which we study with Nicola, have positive kernel, and their semi-additivity is not a question. But this analytic capacity doesn't have positive kernel. Its kernel is complex. So it's not the usual capacity. It's what is called Calderòn-Zygmund capacities. And this is why this property was super non-trivial. And well, Tolsa in his famous paper did it, and he used this result. So it can be found in his paper, or he has a very good book where the chapter is devoted to this result. Okay, so I probably should stop here because it's, I think my time is over. Okay, so thank you very much.
Okay, thank you, Sasha.
Yeah, any questions?
I can't see really. Se qualcuno vuole fare una domanda, mettermi che attacca il microfono.
Yeah, I'd like to ask a question.
Yes.
So in this theorem that is still on the screen here, gamma n of E1 union E2, so the nature of those constants then?
This one?
Yeah, for instance, yes.
In the theorem, I think it's very large.
Mm-hmm.
Almost astronomically large. Well, frankly, Vitushkin asked that. He asked it like with the usual capacities, with constant 1. This nobody knows that, not even close. Maybe it will never be known. I don't understand how it can be done. But yeah, with some finite constant which is universal.
Mm-hmm.
It's done.
Mm-hmm.
Yeah. So
also, if I may, So when you go to higher dimensions,
to high dimensions.
right?
Yeah.
So then, of course, in previous cases, you have the Cauchy transform and so on.
Right.
And now, how do you?
Oh yeah. That's super good question. You see, you can ask. Let me go somewhere. You can ask. So R2 is C, right?
Mm-hmm.
And we have analytic functions. Now, if you ask about other dimensions, the first question which seems natural is C2,
Mm-hmm.
because we also have analytic functions. But in C2, the answer is totally different. It's very strange and absolutely trivial.
Mm-hmm.
So any compact set is removable.
Yeah. Mm-hmm.
Oh.
Solid ball is removable.
Yeah, altogether.
But there you have this strange phenomena that you can fill in functions.
Absolutely, yeah. So
Right.
this is easy and trivial. So we don't even consider that. But if you go to R3, you can ask the same question, and actually R2 should be asked differently. So it's not about analytic functions. It's about harmonic functions.
Right.
Harmonic. Such that the gradient is bounded. You know, gradient of harmonic function is analytic function, right? But in R3, you don't have analytic, but you have gradients of harmonic functions. And gamma 3 of E is supremum of, you go over all such guys, harmonic in R3 minus E, and you take flux. So you go around E and take a flux. So that's the analytic capacity. And there is no Kashi kernel. But what is Kashi kernel? It's a fundamental solution on the plane, a fundamental solution of Laplacian, and you just take derivative. So in R3, you take a fundamental solution, or even in Rn, you have the fundamental solution and you take the gradient. So this is the kernel. So this is the kernel. So it's x divided by x n minus, n minus, no, just n. So, so this is called Riesz kernel. And you need to prove the same thing. So if you have a complex measure with this kernel bounded, then you have positive measure that is kernel bounded. And if you have, so all the same steps. If you have the bounded operator, so this is now a Riesz kernel in L2E to itself, then there exists a smooth surface with this property. And it seems like you can just repeat the everything which has been done before. But you cannot repeat. And you cannot repeat by a very funny reason. So this step is false. So Guy David calls this curse of dimensionality. So this amazing Melnikov's formula disappears. It's not true. It doesn't give anything. You just don't have this part of information. And this is why this part was called Guy David's problem. So he and Stephen Sams wrote two books, maybe like 600 pages together. And books were something like that. So let's go from here. We don't need curvature. We need this. Let's try to go from here to here, from the boundedness of the Riesz transform to the geometric information. Well, it should be n-1, it should be surface. And they started to build a bridge. So this is like a bridge from here to here. And they, so these two books, they consist of like maybe, I don't know, maybe 20 conditions, many of which are equivalent. And they have abbreviations, something like WDPA, ZGSO, something like that.
Nightmare.
So if you have this condition, then you can go from top to bottom. Okay? But where to get this condition? And this is what we did with it's another NTV. So it's now not Nazarov trail, but it's Nazarov Tulsa, myself, we proved one of these conditions. And which means that if these two books are correct,
600 pages.
yeah.
It's a conditional.
No, well, everybody believes that they are correct, but it's 5, 6.
The few things I've read in the book were correct.
No, they're of course correct. It just, if you allow me, I will tell you the joke which belongs to Peter Jones. This is what he said about these books. He said that these books were read by exactly 4 people. So this is 2 authors, Stephen Sams and Guy David, me, Peter Jones, and somebody else. Well, frankly, I was the somebody else, but yeah, well, it's really tough reading.
I had a question.
Thank you.
Thank you. Yes.
I had a question. Okay, you said that this Menger curvature does not work in the real case, right? But
in R3, yeah.
Right. Are there interesting extensions of this Menger curvature to other?
Well, it exists. No. I mean, it exists by itself. It's a geometric notion. It's a very nice thing. It's the only thing that the connection with singular integrals is lost.
It's lost. Okay.
Connection is lost. So by itself, 2 things are interesting still, but they have nothing to do with each other. And this is proved. Well, as much as such statement can be proved, it is proved. There are papers that these things do not have anything to do with each other.
With each other.
In space, right?
Are there other questions? Wait, I'm looking here on the. So if there are no other questions, we thank Sasha again. Thanks for the wonderful seminar.
Thank you very much.
And we keep in touch in the next few days.
Okay. Thank you.
Okay. Thank you.
Thank you. Right?
Thank
Bye,
you.
guys.
Thank you very much.